Hello students, this is your professor Dr. Mink and welcome to the first video lecture for CSC 240 computer organization. I'm recording this during the summer of 2020 because everybody is going to be online 100% of the time in the fall. I'd like to say I've never taught this course online. I've taught quite a few courses online, but not this one, unless you take into account the emergency online we did in the spring of 2020 when New Jersey got locked down. So it's a 200 level course. It's going to be a challenging course. You're going to work really hard, and I'm going to do as much as I can synchronously live with you as possible. I'll hold sessions, I'll answer questions in GoToMeeting to help you get started on various topics. So no further ado, let's take a soft landing into the course. Chapter 1 is really review. It's kind of material you need to have already mastered, but I'll go through it. So let's get started. Thanks. So this course will proceed through various sections, components, modules. We'll talk about, in Chapter 2, a computer and how it processes information. We'll start to associate 0 and 1 with on and off, or the binary numbering system. Chapter 3, we start to understand or explain how the computer works, how transistors, the smallest building block of a microprocessor or a chip, are used to then make up larger microprocessors and other, I guess you'd say, circuits. We'll start to combine transistors into structures that perform operations, and ultimately we'll get into saving information. And we'll continue to combine these larger structures into the von Neumann machine, which is a basic model that describes how all modern computers work. By the time we get to Chapter 5, we'll be ready to start exploring the only language the processor really understands, which is machine language. And we're going to use a simulator called the LC3, which has all the characteristics of a real microprocessor without unnecessary complications. And we'll begin to program the LC3 in machine language, and also we'll side by side we'll be learning machine language and assembly language. And machine language is 0 levels of abstraction away from the processor, and assembly language is a low-level language, 1 level of abstraction away from the processor. We'll get into input and output. We'll be forced to, I say forced to, address ASCII and Unicode numbering systems. You'll love that. It's a pain in the neck. Then we get into traps and subroutines, and ultimately the final topic, which many of you, if you've taken the courses in sequence, have already been exposed to, the stack, which is a abstract data type. So the computer is not an electronic genius. It's an idiot. It only does exactly what we tell it to, and it does not deviate from those instructions. One of the goals of this course is you'll be able to write a program in C, C++, Java, and then really understand the levels of abstraction beneath that high-level programming language, all the way down to one cycle. One cycle of the clock, one machine cycle, if you will, what happens in the smallest increment of time at a microprocessor level. We'll build an understanding from the very bottom of the hierarchy up to a high-level programming language. And we'll talk about hardware in the sense that it will help us to understand the basic instruction set of a microprocessor. This is not an electronics course, but we will delve into the hardware, a microelectronic hardware arena, just so you have the understanding of how the logic circuits support instructions, gates, processors, instructions up to C program, C or C++ or Java, or whatever. It doesn't really matter what high-level programming language we end up using. Next, we'll discuss two very important, critical, recurring themes in this course. First is abstraction, and by virtue of this being CSE 240 and the sequence of the courses you've taken to get here, you should have a fairly significant understanding of abstraction. Okay, abstraction is using something, a device, a program, a method, a function, without needing to know the details of its implementation. Okay, the example here is we can drive a car without knowing how the internal combustion engine works, obviously until you're on the side of the road. You got to check engine light on and the car won't start, but we'll get there. But if you've had basic driver training and you get into my car and I give you the keys and say, drive down, here's $20, drive down and go get us a pizza, and you know where the pizza store is, you could do that. You get in, there's a round thing in front of you. It's a steering wheel. You know what to do with that. There's two pedals on the floor, right? You know what to do with that. And there's a device that slides back and forth in the middle, console that has PRNDL on it. And you know what to do with that. You don't need to know whether the car is a 4-cylinder, 6-cylinder, 8-cylinder, turbo diesel, gasoline engine, hybrid, pure electric. You don't need to know any of that. That's all abstracted away from you. And the second recurring theme is hardware versus software. And we're going to talk a lot about the instruction set architecture. And that is really the architecture necessary to execute the basic instruction set. And the basic instruction set is the machine language. What instructions can the processor, made up of these architectural components, execute? As I mentioned, it's not going to be a hardware course, but we are going to delve into reference hardware. Here's it's old picture, obviously. It might not be an old picture, but it's an old processor, 8080A. Is a very old processor. It had 32K of RAM. Wow. And that processor, that circuitry, was designed to be able to execute a specific instruction set. And I don't know how many instructions that processor could execute, but we're going to study the x86 legacy processor, which was the first 32-bit processor that is really the grandparent, I guess you would, of all modern Windows, Intel type processors. I hate to say Intel because there are other manufacturers, but you get what I mean. It's the most popular instruction set architecture in the world by a long shot. And here is the actual 8088 processor. This was manufactured by Intel. You can see the patents on it date back to 1978 and then again 1983. I know what you're thinking. I wasn't even born. Not me, you. I was born. I was in high school in 78. So Yeah, I've been around a long time, but yeah, I remember I was a senior in high school when we got our first computer in high school. That's how old I am. And the computer club got a grant to get it, and yeah, it was a big deal. And we thought it was amazing, but you really couldn't do much. I think my toaster can do more and has more RAM than that computer had way back then, but I digress. And here we have a picture of the first personal computer, the IBM PC. Um, and This ran an operating system called PC-DOS. And then I don't quite know the history of how this happened, but there was a period of time where there was PC-DOS, which was IBM's version of the disk operating system. And then there was MS-DOS, and obviously Microsoft DOS. Obviously, MS-DOS and Microsoft won the operating system uh, business, and they are now I wouldn't call them a monopoly, but they have quite a stranglehold on the operating system business. Okay, big idea number one: universal computing device. And Alan Turing, a mathematician who came of age in the late 1930s, early 1940s, um, developed a theory that all computers, given enough time and memory, are capable of computing exactly the same thing. Now that sounds hard to believe, but if you really dissect what's being said here, given enough time and memory, those are two very significant tangible constraints. So sure, the processor, if it is a Turing complete processor, and we'll talk about that later, um, the, in a PDA, is that even a term? This is personal digital assistant. I mean, it's probably a smartphone now, but anyway, um, the processor in your smartphone could process the same thing as a workstation or the same thing as a supercomputer, the same task, given enough time and memory. Those are very significant constraints. So yeah, having a processor with a mediocre processing speed and significant enough memory to calculate a complex weather forecast algorithm to determine the chance of rain tomorrow. But if that processor took 48 hours to complete the processing, what good would it be? If you see my point, the point. So yeah, those are really significant parameters, how much memory and how much time is necessary to complete a computing task. Alan Turing was one of the great minds um, of the 20th century. He was a mathematician who wrote a white paper on computation in the late 1930s. He was later recruited by the British government to help break the Enigma code. And he and some other scientists developed the bombe, B-O-M-B-E, which was a device, an electromechanical device that ultimately did crack the Enigma code, which was the encryption system used by the Germans in World War II. And he's credited with saving thousands of lives. Anyway, so he wrote this paper stating that given a mathematical model of a device that can perform any computation, and that model, if you read the paper, white paper, and there's a video link right there, it's uncanny how accurate this paper was in describing modern day computers. And the paper was written in 1937. So it describes a device with the ability to read and write symbols on an infinite tape. My first job out of college, I was a programmer for Boeing. And we actually had, Boeing was a large defense contractor, and they were one of the first big corporations to have computers because they got large defense contracts and could afford the latest and the greatest technology. But back in the archives, there were some computer programs stored on Mylar tape. Yes, Mylar, very large reels of Mylar tape. We didn't use them anymore, but they were there, and it was very interesting for me to see that back at my first job. So every computation can be performed by some Turing machine. That was his thesis. And I'm going to ask you to click on that link and watch that video. I'll also place it in the timeline. It is a fascinating look into the future. So basically what Turing was getting at was a universal computing device. And a computer is a universal computing device. A machine that can implement all Turing machines that is also a Turing machine. Inputs, data, description of computation, etc. So Turing was just laying the groundwork, the foundation. And I often wonder, was he, well, obviously he was laying down a framework that was used. To what extent, who knows? It was used as the blueprint for modern digital computers. And he was also so far ahead of his time in theorizing what such a machine would be able to do so far in the future. So as mentioned earlier, a universal computing device or a computer, in theory, can compute anything that's possible to compute. Now, we'll talk about computable problems later. But a computer can compute anything that's possible to compute given enough memory and time. Very significant constraints. Okay. In practice, solving problems, coming to solutions involves computing under constraints. And I mentioned earlier the weather forecast, the next frame of animation, automotive engine controller, right? One of the first large-scale non-computer computing tasks was electronic fuel injection. And I'm assuming that happened during somewhere around the 1980s. Cars went from mechanical carburation, right? Fuel delivery system that was based on vacuum pressure and various other non-digital inputs to electronic fuel injection. Obviously, the processor had to be quick enough to meter fuel into a high-speed internal combustion engine at the rate necessary to maintain combustion. So it wasn't until, and I'm sure electronic fuel injection was theorized for a long time, but it wasn't until we had fast enough processors to handle, they actually call them micro spurts of fuel and air mixed together and sprayed into the combustion chamber before the spark plug fires and provides combustion and power forward force, if you will. Transformation between layers, big idea number 2. Okay, we have problems that someone chooses to solve with a computer program. Those problems have to be parsed into algorithms, a series of computable statements, and then the algorithm will be implemented in a programming language, and that programming language will compile, it will link, it will assemble, whatever, okay, a series of instructions based on the target instruction set architecture. And I can tell you the small instruction set architecture, maybe it's an 8-bit microprocessor in my high-end coffee maker, which allows it to be programmed to come on at a certain time and shut off at a certain time, and it has different settings for cup size, etc. And it actually monitors when the filter needs to be changed. The instructions for that processor are absolutely positively different than the instructions many of you have written in Java and or C++ or whatever other Python, whatever other programming languages you've learned up until now. That source code that is targeted for the 32-bit or 64-bit instruction set architecture of the PC or whatever. I'm just going to use the word PC as a generic, Mac, Windows, etc., Linux. Okay. And the microarchitecture underpinning that instruction set, the chips necessary designed to support that instruction set are very different than those in my coffee maker, very different than those in the ECU of my car, which controls, all kinds of automated electronic processes associated with that vehicle. And then the circuits necessary to make up the microarchitecture and those individual devices are all different. So, and each one of them represents a level of abstraction away from the previous level beneath it. I think I probably handled this already, but how do we solve a problem using a computer? There's a systematic sequence of transformations between layers of abstraction. You've got the problem, then you design an algorithm and your data structures, and then the algorithm gets refined and implemented using a programming language to express that design. And then a lot of the heavy lifting is done by the compiler, linker, interpreter, and it ultimately converts that Java program, that C++, that Python program into machine language. And that machine language is specific to the instruction set architecture of the processor. If any of you had me for any of the prerequisite courses for this, you know we've talked about stepwise refinement, top-down design. So we could continue to decompose, if you will, each of those sets. So the instruction set architecture, right, is the instruction set that the designer of the processor had in mind, had planned for the processor to be able to handle. And then we choose structures to implement the instruction set architecture. That's the microarchitecture set. And then we need the logic circuit, the gates, and the low-level circuits to implement those components. And process engineering and fabrication. How do we manufacture and develop those low-level components, the actual chip-level components? And it goes all the way down to the smallest building block of a modern computer is a transistor. And we're actually going to have a significant conversation about transistors. So the problem statement is typically stated using natural language. As someone who's worked as a programmer, your problem statement may contain ambiguous and imprecise instructions that have to be clarified, have to be more concisely quantified to so that you can translate that into an algorithm, program, etc. For me, I remember that being a rather frustrating part of the process because although I worked in a very structured environment in the defense industry, doing defense and aerospace work, so it was probably better than most environments at the time that I was actually paid to write programs for someone. Um, this part was challenging because you had your engineering and your design groups or whoever, marketing was involved, sometimes finance, accounting was involved in specifying the problem statement. And that doesn't always make for a problem statement that's easy to translate into an algorithm and ultimately express in, C, whatever programming, high level, low level programming language you're using at the time. And the instruction set architecture, getting from the program to the instruction set architecture is, at this point in time, it's typically a drop down box. What are you targeting? The compile, what should the compiler be targeting this code for? Additional descriptions of each level. The microarchitecture is the detailed organization of a processor, how it's implemented, and there are different implementations of a single instruction set architecture. There was a period of time, and I'm not a hardware person. I've never really been interested in hardware, but there was a time where AMD, Motorola, Intel, all manufactured processors that would run Windows. And I'm really not sure if AMD is still. I know Motorola has been out of the game. I think they've focused on Mac OS, but AMD was a significant player. I know Intel was always the largest player, but you could buy an AMD processor and it would run Windows, and you could buy a Intel processor, it would run Windows, and most of the other chips were manufactured by a series of other companies. Micron was a big, not a processor manufacturer, but the memory, etc. So there are multiple implementations of a single instruction set architecture. The logic circuits, they combine the basic operations to implement or realize the microarchitecture. And there's many ways to implement a single function, such as addition and or not. There are multiple implementations, just like you could buy, I don't know, you could buy I don't know, let's just say a Toyota Camry. You could buy a Toyota Camry and the outside and inside is exactly the same as the one sitting next to it in the dealer's lot. But underneath, one could be a hybrid, one could be a 4-cylinder, one could be a 6-cylinder. Okay. So, and you don't drive them any differently. Nothing different happens when you turn the wheel in the hybrid versus the 6-cylinder versus the 4-cylinder. So, and then devices, you get into properties of materials, manufacturability. Well, that's the edge of this course that we're really looking over into electronics at that point in time. So we'll talk conceptually, vaguely, if you will, about those topics, but it's not really a a core competency of this course. We're going to have an entire lecture or two on basic logic circuits later in this course. Here's some examples, okay, of not, and, or, NAND, and NOR, and the truth tables that implement those logic circuits. Like I said, we're gonna get into this topic at very significant detail. So just stay tuned on that. This slide shows the options or the choices at each level of abstraction. So you've got to solve a system of equations, Gaussian elimination, the Jacobi iteration, multigrid, etc. So they could then be solved in Fortran, C, C++, or Java, and Java. Those could be running on a PowerPC, Intel x86, and Atmel AVR. I've heard of that, but I'm not familiar with that processor. And they could be implemented, as a Centrino processor, a Pentium 4, a Xeon, and then the circuits, you could use a ripple carry adder, a carry look ahead adder, right? And they can be implemented with CMOS circuitry, bipolar circuitry, GAUS. These are all the levels of abstraction all the way down to the circuit, from the problem all the way down to the circuit level. So how will we progress in this course? We're going to start off with bits and bytes, how we represent information using electrical signals and electronic circuitry. How do we build those circuits to process information? And then how do we build a processor out of basic logic circuits? And what operations do we need to implement in order for that to be a logically complete processor? And then we'll get into assembly language and machine language programming. And we'll talk about modular, reusable code, subroutines. We'll get into communication, input, output. How does a processor actually, well, a processor doesn't really actually communicate. There's a handshake between the processor and whatever operating system is managing the peripheral devices. And once again, we'll delve into hardware because we'll have to. And then ultimately we'll look at the highest level, the current highest level of abstraction, the high level programming language, and how do we write, and it doesn't have to be C or C++, that's irrelevant. The author just happens to favor that programming language, but no, we don't. We could talk about Python, we could talk about Java, C, C++, whatever. Okay. So that is the introduction to the course. Thanks for hanging in there with me. I know much of this, some of this is going to be repetitive. It's going to be a review, but it's necessary that you understand all of it so that we could forge ahead into a really complex 200 level computer science course. Thanks. And of course, if you have any questions, don't hesitate to contact me. I'm really easy to get a hold of.